So in this lecture, we are going to look at the solubility rules on Appendix M and then define molecular, total ionic, and net ionic equations. So when you look at Appendix M, you'll see all the solubility rules, what dissolves in water and what does not. And when you first look at it, it can seem quite daunting. It's like, how am I going to ever memorize all that? Well, you don't actually have to memorize all of it. You have to just, I would say, probably memorize the first four, like the most important rules. And if you memorize the most important rules, you'll be able to figure out what the correct answer is. So let's first begin with one of the best rules to remember, and that's nitrates. All nitrates are soluble. So if you're given something like strontium nitrate will dissolve in water. So we put AQ there because we're putting it in water. And we will get strontium ions, and we will get nitrate ions because all nitrates dissolve in water. Okay? What about cesium phosphate? If I put cesium phosphate in water, will it dissolve? Well, all alkalis are soluble in water, and ammonium compounds are soluble in water. So this is an alkali compound, so it will break apart. Okay. What about sodium iodide? Well, sodium is also an alkali, but you could also memorize the rules that all chlorides, bromides, and iodides are soluble in water. So this too will break apart because all iodides, chlorides, and bromides. So when I look at aluminum iodide, I would say, well, it's an iodide, and I know that all iodides break apart or are soluble in water. But there are exceptions to the chloride, bromide, and iodide rule. There are four substances that are not soluble. They are silver chloride, lead chloride, mercury, and copper 1 chloride. So these four individuals will not be soluble, and therefore they don't break apart in water. They just are a solid and they drop to the bottom of the container. Okay? So I would say the rules you need to memorize are the kind of the ones I went over. Another good rule to memorize are the sulfate rules and the hydroxide rules. All hydroxides are insoluble except the strong bases. The acetate rule isn't so bad either. All acetates are soluble except for silver acetate. But the more you memorize, the better. So now we move on to the molecular equation. So the molecular equation is when compounds are represented as molecules. Okay? That's what you're most familiar with from first year chem. Whereas total ionic equations are when all electrolytes are represented as ions. So in other words, if something breaks apart in water, you would represent it as their ions. Then we've got the net ionic equation. And the net ionic equation only includes components that are going through a change. It does not include spectator ions. And what do I mean by spectator ion? A spectator ion means it's present in the solution, but it's not involved in the reaction. It's like in a sport where people are up in the stands watching, but they are not involved in the actual game going on. They're just observing. Okay? So let's do an example of these. And let's start with the molecular. Now let's do the following reaction. I'm going to do potassium hydroxide reacting with iron nitrate. Okay. So this is what you're used to. And you'd look at this, and this is why the molecular is useful, because it helps us predict what the products would be. You'd say to yourself, oh, the potassium is going to displace the iron, and the iron is going to displace the potassium. And that I'm going to have a double displacement reaction, and my potassium is now going to be bonded to the nitrate. Rewrite my charges. The iron is going to be bonded to the OH group. Crisscross, that's what I get. And then I use coefficients to balance the whole reaction out. And I'm going to need a 3 there and a 3 there. And that's kind of what you were used to when you took Chem 1. And the molecular helps us again predict what the products will be, but it can be misleading, especially when we're putting things into water. So these two guys, I'm sorry, are being put into water. Will they break apart? Well, potassium hydroxide is a strong base. And we know that all strong bases break apart. So this is where we are going to do the total ionic. So the potassium hydroxide breaks apart because we memorized the strong bases, and all alkali hydroxides are strong bases. What about the iron nitrate? Will that break apart? Well, that's where you memorize Appendix M. And we know that all nitrates are soluble. Oops, I forgot to have my 3 outside there, sorry. And therefore, this will break apart. There's no 3 there. Now what about the product side? Will the potassium nitrate break apart? Well, we just stated that all nitrates are soluble, so this will break apart. AQ, all of this is dissolving in water. And what about our last guy here, the iron hydroxide? Will that dissolve or break apart in water? Well, when you look at the solubility rules, all hydroxides are insoluble. So what this means is the iron hydroxide will not dissolve. It will be a solid and just drop to the bottom of the beaker. Okay? Then we have the net ionic. The net is your total. So if you have $20 and you spend 8, your net total is 12. So anything that's a net is your overall result. In the case of chemistry, we're going to cross out ions that appear on both sides of the reaction. So when I look at this, I see 3 potassiums on the reactant side and 3 potassiums on the product side. I see 3 nitrates on the reactant side and 3 nitrates on the product side. Those are the only things that cancel. So when you have things on both sides that cancel, we consider they're spectators. They haven't done anything. They haven't changed in the reaction. Everything else is what is actually occurring in the reaction. What's actually happening is the hydroxide ions are reacting with the iron ions to produce insoluble iron hydroxide. So what we really have is a synthesis reaction or a precipitation reaction, not a double displacement like we thought up at the top. So the molecular is helpful in that it helps predict the products, but it doesn't really give you an accurate picture of what truly is happening. So what's really happening is what you have is a synthesis or a precipitation reaction. Okay, so let's just try one more real quick. Let's do let's do lead nitrate with sodium chloride. So the molecular This would appear to be a double displacement reaction. The sodium would bond with the nitrate, and the lead would bond with the chlorine. We erase our charges because we're going to be high-class chemists now. Then we balance our reaction. We're going to need 2 there and a 2 there. We're balanced. Now for the total ionic. So let's represent everything as ions. Okay? All nitrates break apart. All chlorides break apart, except for 4 chlorides, silver, lead, mercury, and copper 1. On the product side, we know that all nitrates break apart. And what about the lead chloride? Well, we know that all chlorides are soluble except for what I said, silver, lead, mercury, and copper 1. So that lead chloride will remain as a solid on the bottom of the beaker. The net, cancel everything that's on both sides, the 2 nitrates, the 2 sodiums, and then what do we have left? We got lead reacting with the chloride to produce insoluble lead chloride. We would say the spectators would be the nitrate and the sodium, because they canceled out and were both sides of the reaction. So this is an example of what you should be able to do, and the next lecture will be on oxidation reduction reactions and balancing those.